The area between two graphs can be calculated using the techniques that we've already studied. For example, if we have the graph of an f function up here and the graph of a g function down here, we have a particular interval, then we can actually find this area between the two graphs rather easily. I mean, think about the meaning of integral in terms of area. When we calculate the integral of f of x within the interval, we're finding the area under f of x all the way down to the x-axis. And if we subtract the area associated with the integral of g of x within the same interval, then we would be subtracting the area under the g function, you see, under the graph of the g function. And so what's left will be the area which is shaded here. So it's the idea that that area is the integral of the f function minus the integral of the g function. We just kind of put the two ideas together and we'll rewrite like this. It's the integral from a to b of f of x minus g of x. Now it's valuable to put them together because sometimes we'll have terms here that can be collected with the terms involved in the g function. And so some efficiencies can be gained by going through this process. Let's take an example or two. Suppose we have y equals x squared plus 2 and y equals x, and we're talking about the interval from 0 to 1. We want the area between the two graphs. Well, here's the graph of y equals x, and here's the graph of x squared plus 2, and the area between them within the interval from 0 to 1 would be this little area. All right, so we go through the process. Now, I think it's pretty valuable to treat this notion of the difference of functions as a formula. That is, we'll write down the situation. The area is the integral from a to b of f of x minus g of x dx. So write that down and then just follow through by filling in with the information from our problem. The interval is from 0 to 1. The f of x function, the top function, is x squared plus 2. The g of x function is the bottom function. It's simply x. And now we sort of put the ideas together. Putting these together, we get this. And let's see, let's integrate. So we integrate here and we get this is the integral function for that expression. And we're integrating from 0 to 1. So let's see, f of 1 means take all of these x's and replace them with 1's, and we get this. And then minus f of 0 means replace the x's with 0's, and all those terms go out. So we have this, and collecting we find that the area between the two graphs is 11/6 square units. Here's another one that's a little more complicated because we're not given the interval in which we want to integrate. That is, we're saying that, gee, the graphs of these two functions intersect, and let's just find the area between those intersection points. You see, we're not given the intersection points here. We have to figure those out. But at any rate, the graph of the 2 minus x squared is this graph. The graph of y equals x is this graph, and we want this area. Now, by the way, when you first look at this, you might think, well, gee, areas below the x-axis are going to be negative, so that's going to throw things off, and we want a positive value for this. What if we lie below the x-axis and all that kind of thing? Well, it turns out that situation is taken care of just by the nature of subtracting those functions. And let me illustrate it like this. Suppose I have an x-axis here and a y-axis. And let's use some rather trivial functions. Let's suppose that we have a constant function for f and a constant function down here for g. Now, and we want the area between them, let's say within this interval. Now, so what we would want, you see, would be the area of this rectangular region. And when we find the area associated with the integral for f, it would be this part up here. And when we find the part for g, it would be down here, but it would be negative. But we're subtracting this. You see, it's f minus g idea, but g is negative, so it's f plus g. You see, so we're adding those areas, it turns out, in order to get that total. So the arithmetic within this process takes care of those situations that seem to become negative. Okay. Now, the first trick here is to find these intersection points in order for us to identify the interval over which we are integrating. And we find those intersection points by solving the system of equations simultaneously. And one way to do that in the simple way here is to solve by substitution. We can substitute in a couple of different ways, but it's real easy to just replace y with x or x with y because of this trivial second equation. Now I've chosen to replace this x with y in the first equation. I solve for y. Let's see, I kick all the terms to one side and I'm factoring, and the zeros of those factors are -2 and 1. And now from there, with these y values, I go back and find x. Well, I find x by replacing y with these values in either of the other two equations, either of the original equations. And the trivial one, y equals x, is the one that I use. So if y is -2, x is -2. If y is 1, x is 1. So the ordered pair -2, -2 is an intersection point, and the ordered pair 1, 1 represents the other intersection point. So this is the point 1, 1, and this is the point -2, -2. Okay, so our interval, the interval in which we are finding this area, is between -2, the x component here, and the 1. So it's within this interval. Okay, now we can set up our situation. The area then is the integral from a to b of f of x minus g of x, and the interval is from -2 to 1, and the top function is 2 minus x squared, and the bottom function is x, and away we go. We put those two ideas together and arrange them in some way that's easy to deal with. And let's see, to integrate here, it's -x cubed over 3, and then minus x squared over 2, and so on. And the limits from -2 to 1. And let's see, f of 1 means replace these x's with 1's, and we get this. F of -2, replace these x's with -2, and we get this. And now just manipulate a little bit, and we find that area to be 9/2 square units. Here's a problem which illustrates the idea that the arithmetic kind of takes care of itself for areas below the x-axis. Suppose we want to find the area that's illustrated here with this shaded region. Now, the curve is x squared minus 3x minus 4, and the x-axis is y equals 0. And all we need to do is make sure that we use the upper function minus the lower function, and everything takes care of itself. Now, we're not designating these intersection points. It hasn't been given to us, so we need to find those intersection points. But that's easy to do because that's just the x-intercepts for the top function. So to find those x-intercepts, we take our function and set this expression equal to 0, replace y with 0, and solve for x, factoring here and finding the zeros of the factors. X is 4 to make this factor 0. X has to be -1 to make this one 0. So the zeros then are at -1 and 4. And away we go. Now remember that with the integral idea, the area is the integral of f of x minus g of x, where f of x is the upper function. But here f of x is rather trivial. It's just y equals 0. It's a constant. So it's just 0 here minus the g function, which is all of this business. Now notice that this minus sign changes the signs through here. So we get all of this business. And now we integrate the integral of all of this business. Now let's move up here. So the integral would be this expression, and here are the limits of our integration. And now replacing, let's see, f of 4 means replace these x's with 4's, and then minus f of -1, replace the x's with -1's. And in writing this, I want to emphasize that in this step from here to here, you simply replace letters with numbers and do no operations. And then after you do this, you begin to perform the operations and simplify and so forth, and you find that area to be 125/6 square units. Now here's an interesting problem, and it's kind of we're marching along the same theme about this idea of area and so forth, but I want you to notice this, that we have an f function, we have a g function, and notice that the f function and the g function too are kind of curvy, especially the f function. So here's our f function, here's the g function, and we want the area between them the area between them. Now they intersect at this point, at this point, and at this point. So we need not only those points of intersection, but we need to be careful that in this interval, the upper function is the f function, the lower function is g. But in this interval, the upper function is the g function, and the lower function is the f function. So we have to take that into consideration as we go through the problem. So let's just kind of hit the high points here. Our first order of business, if we're not given those intersection points, is to find them. Now, to find the intersection points, we generally solve equations like this or functions like this by using substitution. And this is just y equals that expression, y equals this expression. Solving by substitution, well, gee, you know, when your prescription when solving by substitution is to solve one equation for one letter and then replace that information into the other equation. Well, they're both solved for y. So we can just put this y expression in place of that one, or this y expression in place of this one. Doesn't make any difference how you look at it. It all comes out in the wash. So you're setting these two expressions equal to one another and solving for x. Now, it turns out that this drops out rather nicely. It's easily factorable, and the zeros are found to be -2, 0, and 2. So you march over here and you identify those positions. So this is, this is the point -2. You see that it goes down to here. And then here's 0, and this point is 2. Okay, so now we're subdividing our overall interval into two parts. We have from -2 to 0 and from 0 to 2. And so we think about the overall area like this. We say, well, the area is found by adding the two separate areas within those two intervals. So it's the area in the interval from from -2 to 0 of f of x minus g of x, because f of x is the top function. You see, it's the top graph. And then we're going to add the area given by this integral in the interval from 0 to 2 of g of x minus f of x, because the g function has a graph which is above the f function in that interval. So that's how we proceed. Now, in this problem, it does turn out that we get some mileage out of subtracting the functions, and the f function is here and the g function is here, and when we subtract, you see the signs change here, and we can collect the like terms, and it turns out that the collection gives us a rather simple 3x cubed minus 12x dx, and we proceed on from here. I just wanted to show you this part, though, the simplification of this one. The other one simplifies very nicely as well, and we go through the process as we have in the past for the rest of it.